All right, let's sit in silence.
No, we're good.
Okay, so what is today, John?
All right. Particle physics is today.
Mm-hmm.
And
Get the people who weren't here when you were catching me up caught up.
yeah, so we have a few challenges today, right? We're talking about particle physics, and we've talked about particle physics. Like, so first of all,
Send it this way.
what?
The smoke.
Okay. I have a few challenges. So particle physics is super intense of a subject to learn. It's like you don't even really learn it like formally until
It learns you.
it learns. That's deep, dude. That's philosophical.
Super deep. So deep you can't see me.
So, like upper level undergrad, grad school.
Yeah.
So it's complex. And another issue is, we've talked about it before because it's one of my go-to things, like when we're outside smoking. So I need you to act just as surprised as the first
As
time.
episode 3 the first time?
Whoa!
So I need you to, yeah.
I am surprised.
It's alright. I don't remember anything from that episode anyway. I also don't remember.
You trying
any
to say
of
you
them.
don't listen to me when I talk to you?
I'm trying to say, yes, that's exactly what I'm saying.
Okay. All right. So, all right.
Listen, you're technically in the circle.
does that
It's
every
just going to
time.
happen. No, you're in arm's reach, okay? Mike's just far enough away that he's not in the it'd be
He still reaches over
uncomfortable.
his shoulders.
He'll try.
Yeah. So, okay. So, particle physics attempts. I've boiled it down to particle physics trying to answer two questions. What is everything made of on the smallest level? Like, what could I break down everything to where I can't break it down to anymore? Like,
One unit of chair?
Yeah, so 1 unit of chair atoms. Like, what is the smallest piece? Like, does it get
This
smaller?
show is going to be inside jokes from the episode. It's going to be funny to
If
no
you
one.
started here, smallest
Well,
unit of
maybe
chair.
we should just
No,
put
I'll
both
never
up.
stop. First try.
Yep.
Well, we can only host so much data per month.
Yeah.
So it's like, put the good one up. You know what I mean? So we'll have to listen to both.
Well, business. We'll get back to this.
We're
What is
not-
the smallest?
Are we
thing?
actually
Sure.
recording yet? Like, is this the start? Are we started? Are we in now?
Like 3 minutes in.
Are we actually in? I just thought we were doing
cut it whenever.
pre-episode bullshit.
We're good.
Cut it whenever you want.
Yeah, man.
So what were we talking about?
Maybe not recordable.
What's the other
Part-
thing?
Okay, so what's the smallest thing? Like, what is the fundamental unit of chair, right?
Mhm.
And everything else. And is it the same? Is everything different fundamentally, right?
Is 1 unit of chair different from 1 unit of jacket?
Exactly right. So that, and how do those things fit together and work together in order to make everything around us? Right?
Fucking caramel.
Wanted to see. Use my hands because I don't want to use my voice, Rob. You fuck.
All right, so that's what it is, right? What is everything made of, and how does it build everything around us, right? Okay. So you said before that like atoms are pretty small, right? We've talked about it before. So like, let's like work our way down. So we're here, right? Imagine I have a cup of water. Let's figure out the smallest unit of water, right? How could I?
1 waters.
Okay, I want 1 water. So we have a cup of water, and I want less water. So James, what do I do with the cup? What do I do with the cup when I want to make less water?
You drink
Throw
like
it in
You dump it out.
you drink like most of it.
Yeah, those work. Those are good ideas.
You pour it in the toilet.
Now I want you to write it down and hand it in to me. So, all right.
Double
Anyway,
spaced APA format.
APA format. Okay, so we pour out some water, right? You have less water, but we still have water, right? Drops are pretty small, so we could get like a little.
You get 1 drop.
We want to get 1 drop of water, right? But could we get a smaller? Like, is that the smallest water? Is 1 drop of water the smallest water?
There couldn't be anything smaller.
There
than
could
1
not
drop
be,
of
right?
Water.
It'd be crazy that for anything.
But what if we
smaller
cut
than
that
water.
1 drop in half?
Brilliant. This guy's so smart. It's not like we had this conversation ready or not. So, okay, so we break up the drop into half a drop and just start flicking water off, right?
Yeah.
Okay. So you have to use your imagination from here on out, right?
I'm already doing that.
So like your finger's a little wet, right? You got to like keep pulling off water. A molecule of water, you with me? We could get it down to 1 unit of water. A molecule of water is the smallest thing of water that still carries the properties of water. Okay. Now, things get really weird even at this level when we have a molecule of water. Like, temperature doesn't make any sense. You can't have any temperature on this molecule of
There's
water.
no temperature in the molecule.
Right, because temperature is like how much everything's moving, right? And
But
if
a
I have
lot of
one thing,
molecules can hold the temperature.
yes, exactly. It's
But
an
one
aggregate
does not.
thing. One does not, right? So yeah, one
Doesn't
molecule.
hold any temperature. Is not cold or hot.
No,
It doesn't even make sense to talk about it because what temperature is like an average.
I love when you know your question is stupid. Shut up.
So temperature is like the average motion of everything. So if something's hot, shit's just moving around a whole lot, you know? But if you have one thing, it doesn't make sense to talk about temperature. You'll just talk about how fast that thing's moving, right? You know what I mean? Am I talking too loud?
No,
Oh.
no, shut
Okay.
up.
You need to talk as loud as you want.
All right, so smallest unit of water still carries the properties of water, right? But if I break this down any further, and I can, we're going to talk about that I can,
You can.
it's not water anymore. It's other stuff. So
H and O's.
yeah, a lot of H's and the actual letters H and O
Them
is what you
hoes.
find there. The ho. So water molecule is H2O, right?
Yeah.
We've all heard that. That's what it's known on the street as. And so you have
Street name.
so you have an oxygen. Oxygen's pretty big compared to hydrogen. That's what H's and O's stand for, is oxygen, hydrogen. You have one oxygen and two little hydrogens, and they're tacked on to the top, kind of like Mickey Mouse.
With a big thumbtack.
Yes. Yes, that's how chemistry works. Is
They like
big
molecular
thumb.
thumbtack.
Yes.
Big would be crazy.
I want to talk about chemistry. I'm not going to talk about chemistry right now, though. I'm not going to do it. I want
Episode 37, chemistry. Boom.
So, like, where we're at right now is chemistry. Like, why these things even get to look like this? Whatever. We're not going to talk about it. We just keep going deeper, right? So, we're at the molecule now. We break up the molecule. Now we're at atoms, right? We said atoms before. So, we have, as soon as you break it up, now you have an oxygen atom and two hydrogen atoms, and it's not water anymore. We're different stuff. So, we have these atoms, right? And we said before, atom comes from the Greek, which means indivisible. Indivisible. So now we're at the smallest fundamental
Unit of
thing.
chair.
Smallest unit of chair. It's not the smallest unit.
Oh, sorry. It's unit of water. Unit of H and O.
Yes. So, as you might have remember from school, that atoms are made of stuff.
What are they made of?
So if you look close inside an atom,
Yeah, they didn't teach me that in school.
they didn't teach you that?
No, I'm old.
Oh.
They didn't know yet.
That was
They
it.
did-
They didn't know this shit in the
There was
70s.
nothing lower.
It's crazy.
Fuck you.
1870s.
Woo!
I hate old.
Sorry.
Kat is the elder, in case you haven't.
She's like 4 years.
Do
something.
not appreciate being called old.
No, but like, it's a good thing.
We respect our elders.
Um,
Atoms.
Yes.
Indivisible.
Yeah, indivisible, right? So again,
Liberty
I
of
want
us
I
all.
want to talk about the experiments that helped us figure out that we could break this down, because it's so, like, one of the issues with science when we talk about science is I kind of just say things like atoms are a thing, right?
Yeah.
I just say that atoms are a thing, but like, really, a scientist, like a skeptical scientist, should be like, how do you know this? Like,
do
you
you
can
know
tell me, and I do want to talk about it. I do,
Yes.
but I don't. Okay.
Is that a whole?
It's for another time. I actually do want to spend time talking about the experiments of science and how it got us to understand science the way it
Is that an episode on the scientific method?
Yeah, but like real examples and stuff.
Fucking, I'm in. All right, fine.
Okay, so through experiments, you have to take my word for it right now. We will talk about the experiments, but we found that atoms are made of stuff, and they're mostly empty space. Like, mostly empty space.
So atoms are mostly made up of not a bunch of stuff.
Atoms are mostly not anything at all.
So how
But
much?
what is nothing?
But what is nothing?
Wait a minute. Wait. Time out. How much of an atom is, and how much of an atom isn't?
That's a great question, and I hate to say numbers that I'm not 100% certain of, but I'm pretty sure that it's in the high 90s, 95, 6, 7, 8, 9, something like that. That atoms are mostly empty space. Like, that's how much empty space there is compared to the small percent of space.
Okay.
Of things.
Inside the empty space, or rather surrounding the empty space.
Right.
What is the shape of an atom?
Okay. That's such a good question, dude.
I'm trying to find good questions
Okay.
because I asked a really bad one. before.
Okay, so if you've taken chemistry at school, you've probably seen like the nucleus in the middle with those rings around, right? And like it has a circle around, then you have like the electrons in the circle.
Oh, you're gonna have to draw this for the short
Yeah,
one.
yeah. But like, so you see these nice little rings. It looks like a solar system almost. Your sun, your nucleus, your sun in the middle with all the little rings around it. That's nice. That is a nice way to look at an atom. But it's not. It's not. It's not. It's so first. Oh, God, dude.
Yeah.
All right. So
Wait, so we're at what shape is an atom?
So the best way to picture it, like probably the most accurate way to picture it, is that you have your nucleus, and then you have a cloud around it of where you might find an electron, maybe. You good?
Yeah.
You sure?
I love when it's maybe.
Yeah. So
That's my favorite thing.
okay. So now what? Like that uncertainty of where the electron is, like this cloud, where this is quantum physics, and I'm not gonna touch that right now. But that's gonna be a whole nother thing we gotta talk about, like how to describe, like basically your question is how to describe what an atom looks like how could we model it, is quantum physics. We're not going there. We kind of are, but like indirectly. Not
One day maybe.
right. The weirdness of quantum is we're going to talk about another time. Okay, so all right, so atoms are made of protons and neutrons. They chill in the really dense, tight little middle part of why are you laughing at me?
Nothing. Keep going.
What?
You're desperately trying to quietly eat Doritos. And it's been very hard. This whole time. Like, ice cream was a great choice. Oh, Doritos.
You called my name. Here's good.
Crunch.
Give us a loud crunch. All right.
Okay, so that sounds like every eating sound in Skyrim. Whatever you eat, that was the perfect take, right?
Yep, absolutely.
Oh, thank you. All right,
Back on the rails.
back on the thing. All that not getting cut out.
So nucleus, dense, tightly packed. That's where your protons and neutrons chill. Okay, and around the nucleus, spread out, are electrons. Now, hydrogen is hydrogen because it has one proton in the middle. Could have a neutron as well. Doesn't have to. The fact that you add neutrons doesn't make it a new element, right? So hydrogen is just one proton. Lithium is two. Like that's how we get different elements. Is how many protons are in the middle. Yeah.
Radical.
Yeah, radical. So then electrons go around that. That's how an atom's made of. Okay. So this is pretty small. We're at, right? Okay. So electrons are, you can't, as far as we understand today, we can't break electrons any further down. They're the smallest. You can't break up an electron.
So an electron's not made up of other things.
Exactly. Electron, as far as we know, is fundamental. That is one of the fundamental particles.
Okay.
Okay. There's so much I want to talk about. Okay.
No.
So electrons fundamental, but we found out that protons and neutrons, they are not. They can be broken down further. Protons and neutrons. Okay. So we found out that protons and neutrons are each made up of individual particles. There's 3 particles in a proton and 3 particles in a neutron. And those particles are called quarks.
Oh,
Remember quarks?
I heard of these motherfuckers.
Yeah, these motherfuckers, these quarks. Quarks are super weird. They're all weird. Everything's weird in its own way, but quarks are super weird. They also have weird names. So a proton is 2 up quarks and a down quark. Okay?
Okay.
And a neutron is 2 down quarks and an up quark. You with me?
Yeah.
And these quarks, they're fucking...
They're fucking
These fucking
making
quarks.
other quarks.
So you
fucking quarks.
You can't. See, the weird thing about quarks is you can never find a quark alone in nature. You'll never
always
find it
a
alone.
fellow
It
quark.
always has a fellow. It either has a 1 or 2 other ones. So it's either a group of 2 or group of 3. There could be other groups I believe recently we found like exotic groupings of quarks, but you can't find it alone in nature. And if you tried to break up these quarks, right? If you try, like, let's say you grab onto one of the up quarks and you try and pull it away from the rest of the quarks, you have to put so much energy into pulling it apart that you make new quarks.
Mm-hmm.
You know what I mean?
Wait, repeat that.
The entire
How does
thing.
that happen?
No, just the last sentence.
So in order to pull apart quarks, you want to pull it apart. You have to put so much energy into pulling it apart that you make new quarks in the process.
So a quark refuses to be alone.
It
You
refuses
separate
alone.
one
I
from
will
its
make
partner,
a
it
new
makes-
quark if you try to make me alone.
That's crazy.
Isn't that crazy? Okay, so. Alright, so we're at electrons, up quarks, and down quarks. Okay, I'm going to pause there for a second because those three things, electrons, up quarks, down quarks, those three things make up everything that you've ever seen, everything that you ever will
Everything?
see, everything.
Wait,
Everything.
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 Feel that.
All right, so because we just said that everything's made up of atoms,
Yeah.
and the atoms we experience every day are all just interesting combinations of up quarks, down quarks, and electrons.
Wait, I thought we couldn't go. Nope, electrons. Mixing things up. Idiot.
So, now there are more particles. We're going to talk about that. But all the stuff that you experience every day is up quarks, down quarks, electrons. So, like every person, your car you drive, every historical event. Remember we said that every war is just piles of up quarks, down quarks, and electrons just interacting in a weird way. Isn't that weird?
That's
What about those other quarks? Those awkward quarks.
Yeah,
or
the
whatever they're
weird. So the norm.
called. No, I don't know what they're called.
They're
called
weird.
something
Up down,
Yeah.
up down quarks. There's awkward quarks. There's socially inept quarks.
Yeah, there's a lot of stuff. So quarks and electrons. Okay. So we're fundamental now. These fundamental things, these are essentially points, right? Because they're not made up of anything. They're so small. And these things can't, you get super weird when you have to think of things as like the most fundamental particle of a thing, because these things can't spin in the way that you think they would. Because in order to spin, you have to be a composite thing. You have to be able to spin around something, right? But if you have nothing to spin around, if it's only, then there's, you know what I mean? Does that make sense?
Quickly ask why I would think they spin.
Because, I mean, things spin. You could spin.
But like, should I think that all the time?
Because in the pictures of atoms that we always see, they're always spinning.
Yeah, they're always doing weird
The
stuff.
Earth spins.
The Earth spins. But in order, like, if you're a thing, in our world, if
Shit
you're
spins.
in our world, if you're a thing, you could spin, right?
Everybody else in the room was like, yeah, I would absolutely
No, I
think
mean,
that
you're-
shit
It's a
was
good
spin.
question. Listen,
I don't think
no,
it's not.
listen to me. No question is off limits. If we thought there were good questions and bad questions, then like we wouldn't learn
Ask
nothing.
questions.
You know what I mean?
Science.
Yeah, we thought this was a great idea the whole time.
Yeah. still a good idea. I'm good on that for now. Thank you. Okay, so super weird. Fundamental. These things don't have markers either, right? There's no difference between one electron and another electron because they're the same thing. They're the same exact thing. They have the same properties. You can't tell electrons apart. That's kind of weird, right?
Yeah.
Because like
Does
I
that
said,
mean they're identical?
they're identical. Electrons have no markers whatsoever. They're identical things. There was a really far-fetched theory for a while that every electron's actually the same electron.
The one?
Yeah, just bouncing off in weird ways. I don't really understand it too well, but I remember reading about it and thinking that was a super weird thing to think. We don't think that now. We know there are more than one electron, but there's no physical difference between these electrons. There's no any difference between them. Weird, right? They could be in different places, I guess, but that's really it. Okay. So, what was I saying? What were we talking about?
The clone army.
The clone army, yeah. That's what I'm saying.
I don't know.
Okay, so
Fundamentals.
fundamental particles. These are fundamental things. There are more than up quarks, down quarks, and electrons, though. Each of those things has like a big brother,
Yeah.
right? The next generation up, you get strange quark, charm quark, and muons. So the big brother of the top is the strange, I think, and the big brother of the bottom is the charm. I'm not really sure which way that goes. But
Bottoms are always charming.
And then the big brother of the electron is the muon, though. And the only difference between these things, they have the same properties, like same electric charge, everything. They're just more massive, right? And then you go up one other generation. You get top, bottom, and taus.
Yeah.
Taus are the muons.
But does each one actually have a corresponding big brother or whatever?
Yes. So
Then
like,
why don't we ever see that?
okay, because the more massive you get, the more unstable you are.
Yeah.
The less time you exist.
Yeah, that's true.
Before. Man. Well, this has more than one.
We don't fat shame on high science.
We do not. Everyone's accepted here.
Oh, I took that a different way. A different place.
Oh man,
right.
We'll come
we
back
can
to
interpret
that
that
when
all
we're
kinds of
not
ways.
recording.
Back on the rails.
All right, big brothers. Okay, they have bigger generations, right? All right. So, so this is all still matter particles, right? This is still what stuff is made of. That's all this stuff, like the big brothers, the colors, and I didn't even say colors yet. But so quarks have strange properties. They have colors and they have flavors. I don't know who was on the naming committee for everything that has to do with quarks, but everything about them is ridiculous. The flavors, the name quark, and like the whatever. Okay, so the difference between quarks and like leptons, which are electrons, muons, and taus, right? So we have categories for these things, right? Mm-hmm. I'm saying a lot of words.
Yeah.
So leptons are like light particles, like L for light, and then it's the electrons, the muon, the tau. They don't.
You say the tau, do you mean like the way?
That's like the Eastern tau.
What
That's
is...
TAO. But I'm saying tau like the Greek letter, which is TAU.
Okay.
Okay. Physicists love Greek letters.
We've left all of my schooling at this point. I'm in new territory. Completely new.
Physicists love Greek letters because when we like mathematically do everything, we ran out of the alphabet real quick. So we started dipping into Greek letters, and we use Greek letters to name shit. That's really the only reason why.
Oh.
Muon is mu, and this is okay.
Yeah,
we're
maybe
losing.
wasn't a good idea. Shit, we don't even have triple digits of letters. Like,
then you have to start doing subscripts and
yeah, it's like A B.
Yeah.
Fucking what?
Right. So like, but let's just like contextualize this for a second. I'm saying a lot of words, but there's a lot of shit going on, and we're just trying as humans to put them in boxes so we can talk about it, right? So when I see this thing going on, that's an electron. When I see that thing going on, it's a muon, right? Okay. For a long time, we thought it was just up quark, down quark, and electron. But then we started like discovering new shit. We realized that there are other fundamental particles out there than the ones that we generally experience every day. And like I said, the more massive ones, they're there, but they break down quickly into the lower mass brothers of themselves. You know what I mean? So like the muons will break down into other things like that are less massive because it's more stable.
So
Yeah.
where
You with
do
me?
all the other electrons go?
The electrons?
Like they're just exponentially increasing?
We're not creating. So, okay. Energy in the universe is conserved. Mm-hmm. We could all get behind that, right?
Yes.
That's one of like that is like, I think that saying that energy is conserved is probably the most fundamental thing that you could say in physics. Like that is like where we base everything on. So if we found out that wasn't true, that would be a big deal. That would be a big thing.
Big kick in the nard.
Yeah, so
Shit, we're wrong.
but like
Oh,
no, listen.
Burn
if
the
we,
books. We're starting
if we found
throw it
that-
all away. Throw it all away.
But listen, if we found that though,
How do we get to the fucking moon? Luck? Jesus.
See, that's the thing though. But like, if we found out that energy wasn't conserved, that fundamental thing, first we would probably be like kicking the nards, right? That'd be like, what the fuck? But also, that'd be super exciting because we found like more fundamental aspect of nature than we've even thought possible, right? That's when the scientists get excited. When when we completely 180'd on what we thought was going on. Like they're like, oh, we have shit to do now. We have work to do.
You had like a sciencey creep face on when you said that. You're like, oh, we 180'd. You're like, oh. I love it.
So
Gravity's
and that,
not real.
and like that would be a great question. Like,
Freak
how
your way
did
out.
we get to the moon if like our fundamental basis of things was wrong? All right, we're going off topic, but okay. So fucking fundamental stuff, right? These are the fundamental things. Smallest thing. This is matter particles, right? Those are called fermions, and the reason why that they're separate from the other type of particles we're going to talk about is that they take up space. These type of particles take up space, which you would think that if it's a thing, it takes up space, right? But the other particles do not take up space. You could dump as many as you want in a singular spot. You can have thousands. I'll get there. Let's say with the fermions, they take up space. The reason why they take up space is because of quantum physics, and I can't really. They take up space. You just have to like. You're with me that. So in order to have stuff, you have to take up space, right? Yeah. Okay. Okay. One more thing I got to say about quarks before we move on to the other types of particles is that quarks are different from leptons because they interact with the strong force, which means that like leptons aren't in the nucleus, but the protons and neutrons in the nucleus because they have the gluons sticking them together. Remember?
God, I love the gluons.
The gluons. Okay. Those are fermions. We're good there. So now the bosons are the other types of particles. And these are weird names because you had a guy named Fermi and you had a guy named Bose, and they just got the names of the particles. So we have the bosons. The bosons don't take up space. And bosons are your force-carrying particles. Bosons are the reason that the universe is interesting. Because
That's the reason?
that's the reason.
Oh,
because
fuck.
if it wasn't, if the matter particles didn't interact with each other through the bosons, they exchange a boson to interact with each other. So every time gravity happens, is because the particles are exchanging gravitons. Gravitons, they're called. They're exchanging gravitons, a boson that's making gravity occur. You're coupling with gravity. You know what I mean? Like electromagnetism, like when you have two like charges repel and different charges attract, it's because they're exchanging photons, which is the light particles. Remember we talked about the photons?
Yes.
They're exchanging photons. So if their bosons didn't exist, then you have these matter particles just going in straight lines forever and never interacting with one another. You would have individual quarks because there's no bosons to tie them together, right? The fact that we have anything at all is because of the bosons. Okay?
Yeah.
That's a big thing, right? The fact that, okay. Bosons could pile on each other, and the forces are carried through the bosons. I said gravity was graviton, electricity was photon, electromagnetism, and then you have the strong and weak nuclear forces. I won't really get into them too much, but the strong force is what makes nuclei. The reason why atoms have a nucleus at all is because of the gluon and the strong force, right? The weak force is the reason why radioactive decay occurs. Is one of the things that you think of it, right? The radioactivity happens because of the weak force. The strong force is pretty strong, and the weak one's not as strong.
So the weak force is like losing electrons?
The weak force is so remember everything has a boson.
Yeah.
The weak force is mediated by the charged W bosons, positive and negative, or the neutral Z boson.
Okay.
Okay, and there's a different interaction than any other stuff.
Okay.
All right, good. How's everyone doing? That was a lot. That was a lot of stuff. So, okay. Now, the reason why we know this, I do want to talk about this for a second. The reason why we know this is in order to figure out what's going on at the smallest level, we've had to build the biggest machine that humans have ever built ever. Mm-hmm. And these are the particle accelerators, right? The Large Hadron Collider in CERN, in Switzerland, it's so big that it crosses the Swiss-French border, this thing. So we had to build the biggest machines, and in order to figure out what's going on inside these particles, we have to speed them up and slam them into each other in order to figure out what's going on. Now, I'm going to say something, and you're not going to understand it.
That's
Okay?
it's totally different than the
gonna-
rest of the time.
I'm going to say it, but I'm going to say it, and you're not going to understand it, but I'm going to try to explain it as best I can after that, okay?
Yeah.
That's going to be the progression.
Yeah.
You ready?
I'm gonna do it.
Okay. We smash particles together, see what comes out in order to figure out what's going on the inside. But it's not that we're breaking it apart to see the pieces. We're slamming them together to make a shit ton of new particles and seeing what kind of new particles come out of it. So we're making stuff by smashing stuff together. Right? Did you understand that?
Yeah.
Did you, though?
Yeah, you smash stuff.
To make stuff.
Make stuff.
Yeah. So that was the thing that doesn't make sense.
Yeah.
Okay. And in order for that to make sense, I have to tell you where particle physics lives as an idea within physics. Okay? You ready? You with me? So there are 4 realms of physics that kind of follow different rules, if that makes sense. Or essentially they all follow the same rules, but they kind of follow different rules. That's really what I understand right now. Classical physics is like the physics that we've understood since 1600, and that's where we live. It's slow moving and really big, right?
Yeah.
Okay, that's classical physics. Special relativity, we talked about the first episode, right? That's when you have big stuff moving at close to the speed of light. So now we're getting faster, right? That's like the other realm of physics, special relativity. Another realm is if you have really small stuff not moving that quickly. That's quantum physics. Okay? So you have really small stuff not moving that quick, right? That's when really weird shit happens at that point. So now, what if you have the really small stuff moving at close to the speed of light? That's the last realm, and that's the really complicated one. And that's called quantum field theory. Okay? Okay? Mm-hmm. You good? Particle physics lives in quantum field theory. It's really small things moving super fast. So it has all the weirdness of quantum and all the weirdness of fast-moving things. So everything that happens here is very counterintuitive. It's not what we experience every day. But the weird thing is, it's like it still follows rules, though. It still follows rules that we could like at least predict what's going to happen, right? With the explanation we have, what's going on there. So even though it doesn't make sense, it's working for how the kind of experiments we're seeing coming out of this, right? All right. So you can think of things as particles. Or you could think of things as a field and a vibration in that field. So the best way to sum it up without getting into the weirdness is if you're looking at it, if you're looking for it, you could look at it as particles. But if you're not looking for it, you can think of things as waves and fields. Depends if you're looking or not. You with me? Dude, shit gets weird at this point. Shit gets super weird. And it's weird that our actual like measuring it or not measuring it changes like how we could describe it. But yeah, how are you? You okay?
How do you look at it when you're not looking at it though?
So, it's a good question. So that's a good question, man.
Are they lying about all that? I don't know.
Isn't it like you could only look at one of the variables at once?
Yeah.
Like you could look at like where it is or
Yeah. That's the
with
quantum
the
thing,
one.
right?
Yeah.
So you can either know a lot about where it is or a lot about how fast it's going. But you can't know both at the same time. All right. So everything is a field, right? So you have an electron field, and an electron is really just a vibration in that field. And if you're looking at it, it follows all the rules of particles, but if you're not really looking, it's like a vibration in a field, right? So when you have an electron, you have a vibration in the electron field. And everything is hanging out at like a zero value, right? But because of quantum physics, how weird it is, you have some fluctuations going on, right? So when we have, remember Einstein said E equals mc squared?
Yeah.
You learned that or whatever? That's just saying that energy is mass. Mass is a form of like energy, right? So when you're taking these particles, you're moving them super fast. They have a lot of energy, right? And when you smash them, you're trying to vibrate the other fields to see what like pops out of it, right? When you have that much energy, you could disturb the other fields, and then that's where particles come from. So like when you're saying these particles are popping up out of nowhere, you're really vibrating that field, and that's what pops a particle into existence. Does that make a little more sense?
Yeah.
Okay. Okay. There's also the Higgs boson.
Easy. It's gonna be easy.
Yeah, this is the last thing the last complex thing we're gonna talk about. Okay. This is all super tough, but like the Higgs boson was a big deal. Like 2013, we discovered it. Like recently, it was a big deal. The Higgs boson is what ties our idea of particle physics together, right? Mm-hmm. But like it's also like us finding it and looking for it is also kind of like the frontier for where else particle physics can go. Because like the standard model works really well, but we're looking for new ideas to describe things that we can't describe yet, like dark matter, dark energy, like the stuff we don't have an explanation for, the answers we don't have. We're hoping that like the Higgs boson is our door into understanding other stuff. Okay. The Higgs field is not at zero. It's at a higher value. And the fact that there's a Higgs field is the reason why things have different masses, actually. Because it's moving through, because when you move... All right, I'm going to put a pin in that. You good? There's a lot of stuff. There's a lot of stuff.
Pin it.
Okay.
Pinned.
Last thing I do want to talk about... How much time do you have?
You're at like 30.
Okay. Last thing I want to talk about. I want to talk about why we're even bothering with all this, right? I said a lot of stuff. There's a lot of stuff going on in particle physics, right?
There's a lot of stuff.
There's a lot of things going on.
You seen all this stuff?
And all the time, whenever particle physicists are being interviewed, at some point or another, the interviewer always says, well, what's going to happen? What are we going to get out of this? Why are we pursuing this at all, right?
Yeah. Why?
And
spend my hard-earned tax dollars.
Right, exactly. Like, what are we gaining out of this, right? And it's not, we're not doing it to gain anything else but knowing the answers, right? Like, we're trying to figure out what's actually happening here in our world, right? In our universe.
We could take over space.
We've never done science to get something out of it. There's a famous... Well, we're not 100% sure if this interview happened or not, but it's a good story, so I'm going to say it. Michael Faraday, was doing a lot of work with electricity. And when he made all his discoveries with electricity, he was getting interviewed, and he said, the interviewer was like, well, what is this electricity thing going to do for us? And Faraday's like, I have no idea. But if it does something, I guarantee you the government will find a way to tax it. And like, where are we now? We're sitting with this thing that's picking up what we're saying with these beautiful lights. Like, you know what I mean?
Transmitting it to the universe.
Yes. So yeah, we do get good things out of it, right? The World Wide Web happened because of particle physics. Because we needed a way to share this data, all this data that we're getting from these particle accelerators. So we wouldn't have the World Wide Web if it wasn't particle physics. These things happen. They come out of science. Positive things happen, but that's not why we're doing it. We're doing it because we're satisfying our like core human value of curiosity, right? When you're a kid and you're looking at your parents and you're like, why is the sky blue? You're not asking that question to get something out of it, that you'll gain some tangible thing from knowing why the sky's blue. You just need to know, why is it blue and not another color? You know what I mean? Why are some things hot and other things cold? Why is the universe set up the way it is, you know? That's a very core human thing. And the reason why I love particle physics so much is it's like they're not trying to like sell you anything. There's no ulterior motive, you know what I mean? It's like they're just kids trying to figure out the Lego blocks of the universe, you know? That's really all it is. And they're spending their whole lives and everything they have to satisfy that curiosity to, you know, bring us forward in our understanding. And what comes out of it is all good and stuff, but that's really what it is fundamentally. You know,
knowledge for the sake of knowledge.
Yes, right.
I want to know it.
And there's a lot of stuff we don't know about particle physics yet, but we're learning as time goes on, as we keep cranking up the energies of these particle accelerators.
Smashing shit together.
Yeah.
And learning.
Okay. We good?
Oh, yeah. I desperately want, you need to like
I was lost
capture
so hard
the
in
part
the
where
like
he goes,
halfway through that.
there's no ulterior motives. Just get that piece and save that for things.
For things and stuff.
Things I need.